This Sunday morning, I awoke to a beautiful snowstorm, and I decided to cook a really great like veggie scramble, and I turned on some jazz, and I just ate a really nice breakfast, and my insulin levels went up, and of course my liver was thanking me because it now could activate the glucokinase enzyme and store away the extra glucose from my lovely breakfast as I went into the rest and digest phase. So this is a very out of scale depiction of the liver where when my glucose levels were high and insulin levels were high, glucose was transported into my liver and was converted by the glucokinase enzyme to glucose 6-phosphate. That glucose 6-phosphate could then be converted in an isomerization reaction catalyzed by the enzyme phosphoglucomutase to the intermediate glucose 1-phosphate. And glucose 1-phosphate is the precursor metabolite for the synthesis of glycogen. It actually takes another step before we see glycogen being built. There's an enzyme called UDP glucose pyrophosphorylase, this enzyme here, that catalyzes a conversion of glucose 1-phosphate into UDP glucose. That UDP glucose, high in energy, can be converted, can be then added as the individual monomers added to a glycogen chain. So then glycogen, of course, holding on to the excess energy that I now have. So if I manage to get through my biological chemistry preparation and all my other work today, then I just might have time to go for a ski. In which case then my glycogen will become one of the most important sources of energy to power my exercise, and then that will be broken down. So the enzyme that catalyzes the conversion of UDP glucose to glycogen is very fittingly named glycogen synthase. The enzyme that catalyzes the breakdown of glycogen to glycogen 1-phosphate when I do start to ski and use up my glycogen stores is glycogen phosphorylase. Now, very fittingly, glycogen synthase and glycogen phosphorylase are reciprocally regulated. That is to say, when one's turned on, the other one's turned off. So hopefully you've never had a relationship like that. But this is very convenient because, of course, you wouldn't want to be synthesizing glycogen at the same time as you were breaking it down. So if suddenly the need for glycogen becomes high, glycogen synthase is inactivated and glycogen phosphorylase starts to do its job. We'll look at details more soon. So, of course, then this reaction converting glucose 1-phosphate to glucose 6-phosphate is a near equilibrium, and so it just occurs when reactant is high and pushing towards the glucose 6-phosphate. And then finally, that glucose 6-phosphate can get converted into glucose. Remember that there aren't a lot of tissues that have the enzyme glucose 6-phosphatase, but your liver is one of them. So in the liver, the kidney, the pancreas, and the small intestine, we see this capability of converting glucose 6-phosphate backwards to glucose. Now, this is really, really important. It's very important to me when I'm going skiing because I want to know that my liver is going to serve as my food bank for my muscles, that I can take that glycogen from my liver and I can get it delivered in the form of glucose to my muscles. Of course, my brain is also really happy about that too because it runs on glucose, many parts of the brain, and it requires that glucose from being delivered from the food bank, the liver, to the brain. So in actuality, glucose 6-phosphatase in the liver, in liver cells, in hepatocytes, is located in the inner leaflet of the endoplasmic reticulum. So if we want to, we can grab this reaction so that we're not confused, that we see that it in fact does occur in a different compartment. So in the endoplasmic reticulum, so if we might just say that this is crossing into the ER, so if I can kind of draw a really sketchy ER here, recognizing that reaction occurs as the glucose 6-phosphate is passed across the membrane of the endoplasmic reticulum, converted then to glucose. So within the endoplasmic reticulum, then we see the formation of glucose. So forgive my writing here. that this is just glucose. And then that glucose can be included in budding vesicles off of the ER and shipped out of the liver and sent to other tissues, including muscle tissue or brain or others. So that liver is providing glucose, is serving as the food bank of our bodies. So we can look at what might be happening in muscle tissue, where that glucose is delivered to the muscle tissue. And if I am skiing when this delivery takes place, which I hope I will be, then I would be seeing the glucose enter into my muscle tissue, get converted to glucose 6-phosphate, and be utilized as energy in glycolysis and the TCA cycle. Now, if instead there's just an excess of glucose and I'm looking at a type, like a slow twitch muscle fiber, which those are the ones I develop a lot of from a lot of endurance training. So a slow twitch muscle fiber, it's important to also note that if there is a lot of glucose, say after my wonderful breakfast this morning, that my muscle tissues can also store a certain amount of glycogen. Now, what muscle tissues cannot do is convert glucose 6-phosphate backwards into glucose. So muscle tissues are not food banks in our body the way that the liver is. But that glycogen that was stored away, so one could say it this way, that when I start skiing, there is a certain amount of glycogen stored in my muscle tissue itself that I can utilize to power my energy needs. Fantastic. So this gives us a sense of glycogen synthesis, glycogen breakdown. Let's learn a little more. Let's go ahead and take ourselves to a situation where glycogen is getting broken down. That is, we're looking at glycogenolysis. We're thinking about a need for energy from our liver storage. So we know that glycogen phosphorylase is going to be active. Of course, glycogen synthase will be inactive. And I want to take a zoom in look on how glycogen phosphorylase acts to cleave the 1,4 glycosidic linkages in glycogen. So here I've drawn a picture of glycogen where I'm ignoring the branch points, the 1,6 linkages, and focusing in on the 1,4 linkages because those are the linkages that glycogen phosphorylase targets and breaks. And rather than hydrolysis that we would see as maybe a typical breakage of that 1,4 linkage, glycogen phosphorylase uses something called phosphorylases. So not hydrolysis, but phosphorylases. And so that means that the recipient in that group transfer is going to actually be the phosphoryl group that will eventually be transferred onto the glucose residue to make glucose 1-phosphate. I'm going to actually jot this down and show this in action. The phosphorylases of this bond, the breaking of this bond, to then form the product, which we know will be the glucose 1-phosphate. Plus, of course, glycogen and -1, because now one residue has been removed from the non-reducing end. So maybe you're thinking to yourselves, well, what is this enzyme, this epic glycogen phosphorylase? What does it really look like? I'm going to actually draw a quick cartoon depiction of the enzyme. It is a 2-subunit enzyme. It is a dimer, that is to say, and it has kind of this neat structure, kind of a bulb there, and this is its active site. So here's the active site. But of course, remember, it is a dimer, right? So we're actually going to see another subunit that looks quite similar to this subunit, only basically almost inverted. and we won't worry there that we're a little bit off the page. But what's cool is that at the interfaces, this actually forms some really important sites. So here is an allosteric site. So we are going to see if regulation by effector molecules at this allosteric site. And of course, one on each of the two subunits. And of course, we've got another active site here on the second subunit. Of course, that's where the glycogen binds and where phosphorylasis takes place. But not only is this enzyme regulated by allosteric, maybe feedback inhibition, and I want you to be thinking about what could be the feedback inhibitors, it also is regulated by covalent modification. So how beautiful is this to see in action, as I mentioned, that there could actually be both types of regulation taking place simultaneously. So we also have a phosphorylation site where covalent modification can take place. So a phosphoryl group could be added, and that would modulate activity. And in fact, it actually turns out that that is the most important form of regulation within the glycogen phosphorylase enzyme. So let's take a look at the fact that maybe ATP would be a molecule that would bind at that allosteric site and serve as a feedback inhibitor. So it might bind there and negatively or feedback regulate the phosphorylasis, because of course if there is no need for ATP, then why break down that precious glycogen store? Save it for another rainy day. Now, by same argument, one might guess that in fact maybe if ATP feedback inhibits, maybe AMP and ADP serve as effective activators of glycogen phosphorylase, saying, make more ATP, we're getting high, there's need for more ATP. So maybe we could also think about those as being effective feed-forward activators.
Remember that glycogen is a highly branched polymer of glucose, so every 8 to 12 residues there's some branch point at which we see a glucosidic linkage that is a 1,6 glucosidic linkage. So let's look at how glycogen phosphorylase attacks this molecule and why it is that glycogen phosphorylase needs some help. It can't do it all by itself, and in fact there's another enzyme that will help it entirely degrade this molecule, taking care of the branch points and everything. So in comes glycogen phosphorylase, and it always is going to chew like a Pac-Man type enzyme from the non-reducing end down. So it'll chew off, and it will do so on the branch point as well. It'll take off this glucose first, converting it to glucose 1-phosphate, this one next, and it'll keep on chewing down that string of glycogen moieties until finally it reaches 4 before a branch point. So let's see that happening here. It's going to chew off this one first. Boom. We're going to see that get removed. Okay, that'll be converted to a glucose 1-phosphate. This one will be next and get converted to a glucose 1-phosphate as well. Okay, these are just getting broken down, leaving a shorter and shorter glycogen molecule, until finally we are 4 before the branch point, almost there, one more to go. Glycogen phosphorylase just going at this. Same thing on this. We're going to see one at a time chewed off by glycogen phosphorylase. Okay, cleaving and making all of these are going to be glucose 1-phosphate moieties. Okay, so getting close here. 1, 2, 3, 4. One more. Excellent. So 4 before the branch point, glycogen phosphorylase is basically going to turn its nose up at all of this, and it's going to say, forget you, I don't do branch points. And in comes another enzyme that's going to help it out with the branch points. So this is going to be, this enzyme is going to be working on what we term a limit dextrin. So once glycogen reaches this point where there are four residues away from the branch point, this is now termed a limit dextrin. So that's what we have at this point. So at this point then, a bifunctional enzyme called the glycogen debranching enzyme, it's going to come in and say, hey, glycogen phosphorylase, you wuss, I'm going to take care of this branch point, no problem. And what it does is really kind of interesting because it's got multi-activities in it. And the first activity is actually a gluconeotransferase activity. So this gluconeotransferase activity is basically going to pick up this group of 3 and relocate it to the end of the main strand and allowing now glycogen phosphorylase to come back in and continue cleaving on down the line. However, this still leaves this one glucose residue attached via a 1,6 linkage, and that's where the second activity of the enzyme comes in, the glycogen debranching enzyme comes into play. It has an amylo 1,6 glucosidase activity that's actually going to cleave and remove the remaining linked glucose. So it's going to remove this glucose here and release that moiety. Now what's really interesting though to note about this is that the amylo 1,6 glucosidase activity of the debranching enzyme doesn't form glucose 1-phosphate. So this one glucose that was attached by the 1,6 linkage at the branch point is not worth as much energy. And I want you guys to think through that. So at every branch point there's one glucose worth less activity. So think through that. I want you to think through how many ATPs can be made from the glucose converted by glycogen phosphorylase to glucose 1-phosphate as opposed to the free glucose that's released by the amylo 1,6 glucosidase activity of the debranching enzyme.